Ladies and gentlemen, I have some data on the screen that shows the force and velocity graphs after I have pulled the block across the table. Um, I can't tell because the scale is so large on the velocity time graph, from about negative 50 meters per second to positive 50 meters per second. I can't tell whether or not this is a constant velocity. I have data that's constant velocity or not. The scale is just too large. So I'm going to go in and I'm going to alter the scale on the velocity time graph so I can get a better feel for what the trend is. So in order to do that, I'm going to have my cursor active inside the velocity graph, and I'm going to do a two-finger click inside the velocity graph, and I get this list of choices. I'll come down here and I'll click the auto scale button and just zoom over to the auto scale, the plain auto scale. Do not choose auto scale from 0. When I do that, then my graph then zooms way in and I get a really nice picture that I can make some sense of. This period right in here clearly is not constant velocity. Velocity is changing a great deal in these peaks and valleys, so there's tons of acceleration right in here. So I would not have I would not be able to make any conclusions about the applied force being equal to the kinetic friction in this period. It does look right here, though, as though I have a really nice, steady, constant velocity. I'm going to do something right here called a linear fit, and I'm going to see whether or not I have very much acceleration. If I have an acceleration that's close to 0, then I can assume that this is indeed a period of constant velocity. So in order to do that, I'm going to take my cursor and drag it over the period that I think looks very linear. And I'm going to let go after it's highlighted the chunk that I like and suspect is constant velocity. So I've highlighted that in a light blue. And then I'm going to take my cursor up to the top and I'm going to choose this linear fit function. Notice that the label has shown up that says linear fit. So this line right here, I'm going to click on this function and I'm going to get a linear fit for the portion of the velocity graph that I highlighted. So now if I look at this box, I move it over here, I see that I have a slope on this graph of 0.008505 meters per second per second. So based on that unit, this is an acceleration number. So I have a very tiny acceleration during that period. If acceleration is 0, then velocity is constant, and it's reasonable to assume with this very, very small acceleration that acceleration is essentially 0 during this period. So this is exactly what I'm looking for. I like this as data that I can pull off from my force graph. Now be very careful next, because notice that on the velocity graph, the time axis goes from 0 to 6 seconds. On the force graph, the time axis goes from 0 to 10 seconds. They're not aligned. Sometimes they will be. Yours may be aligned, yours may not. But if it's not aligned, then what I just showed you will help you with that. This blue area that's highlighted on both graphs is the same time interval. So this one starts at about 2.9 seconds, or about 3 seconds rather. I know it starts at 3 seconds on the velocity time graph because I've got my cursor sitting there at the front of that blue period. And if I look in the lower left-hand corner of the velocity graph, there's a coordinate pair. That coordinate pair is 3 seconds, comma, negative 0.440. So that first coordinate tells me that that's 3 seconds. Then if I bring over to the other side and look back at that coordinate pair in the lower left corner of the velocity graph, I see that I have about 3.52 seconds and approximately the same velocity value. So that's what I'm looking for. So my velocity during this period, I need to record that. My velocity during this period is going to be approximately 0.49, possibly 0.5. I think we could round it to 0.5. So my velocity is 0.5 meters per second during this time interval. Let's go up here now on the force graph and determine what the force was during that period. So if I, again, put my cursor over the position where I want to get the force reading, on the force graph in the lower left-hand corner, you see again a coordinate pair. The coordinate pair is the coordinate pair is 3.01 seconds, comma, negative 4.9. So at 3.01 seconds, the applied force was negative 4.9. If I scoot over in that interval, later on at closer to 3.5 seconds, notice that the number in the coordinate pair now is 3.47 seconds. At 3.47 seconds, the applied force is negative 4.8 newtons. So I think it's reasonable to assume that during this period from 3 seconds to 3.5 seconds that I have an applied force of approximately 4.8 newtons. The negative sign simply told me the direction of the force. I'm interested really here in magnitudes. So the fact that that is a negative value is not particularly relevant. We just know that we had a 4.8 Newton force. It happened to be applied in the negative direction, but we were just looking for that magnitude. Because since I know my applied force was 4.8 newtons, then I know that the kinetic friction force was also 4.8 newtons. So bada bing, bada boom, I got what I needed.